Hello, welcome to this video where today I'll be going through the OCR AS Level Chemistry 2022 Paper 2 Depth in Chemistry paper. And without further ado, let's get into this video. So let's go ahead and look at the first question. Lime is a citrus fruit containing citric acid, C6H8O7. Citric acid is a weak organic acid. What is meant by an acid? So an acid is basically, it releases... it releases H plus ions in the solution. So yeah, that should just be memory recall, to be honest. And what is meant by weak acid? Well, it partially dissociates H plus ions. Oh, that looks like a no. H plus ions in the solution. Right, part B. A student carries out a titration to determine the mass of citric acid in a lime. The student follows the method below. Squeeze the juice out of 2 limes. So we know there's going to be 2 limes here. So just keep that in mind. Transfer the juice into 250 centimeters cubed. Also keep this in mind as well, because you're pipetting it into 25 centimeters cubed. So when you work out the moles, we know we'll have to multiply by 10 to get it back to the 250. Titrate this solution with 0.8 moles per decimeter cubed of sodium hydroxide. And here we've got some titration results. Right, record the student's burette reading, calculate the mean titer. Right, so obviously to work out the titer, you do the final reading minus the initial reading. And to find the readings, what we'll do is we'll look at where the meniscus sits. And from there we can work out what it is. So if you use titration 1 as an example, you have the bottom of the meniscus here, which would be 0.05. And if you look at the bottom of the meniscus here, you have, well, this is 27.1, this is 27.2, this is 27.3. And as is between 27.3 and 27.4, obviously in between that will be 27.35. So we know that the final reading is 27.35 for titration 1. The initial reading is 0.05. So if you do the final reading minus the initial reading, we should get 27.30. So make sure you do it to 2 decimal places in this, or if in any other scenario, the same significant figures or decimal places, usually 2, because whenever you're inputting data in the table, you need to keep the accuracy of the numbers the same. And so, like, say you're doing a practical write-up, for example, then you'll have to do this. Sometimes they may not give you a mark if you don't do it to the correct decimal places. So always make sure that you do it to correct decimal places. Anyway, titration 2, let's have a look. So let's see where the meniscus sits, which sits at 0.1 in this case. And over here sits at 27.1, 0.2, 0.3, 0.4, 0.5, 0.6. So it's between 0.6 and 0.7, so it'll be 27.65. And so we know that the final reading is 27.65, initial reading is 0.10, and so the titer would be 27.55. Right, now looking at titration 3, we can see that the meniscus sits at 0.1, 0.2, 0.3, 0.4, 0.45, and the meniscus here sits at, well, if that's 0.5, we know this is 0.2, it's 0.7, 0.8, so 27.85. So what we can do is we can do 27.85 minus 0.45, which gives you 27.40. So that's what we know the titer is. We know that the final reading was 27.85. And the initial reading was 0.45. Right, so now we need to work out what the mean titer is. So working out the mean titer, we need to find the average between the concordant results. So ones are plus or minus 0.1 from each other. So in this case, it will be 27.30 and 27.40 as they're plus or minus 0.1 from each other. So we can do 27.30 plus 27.40. Divide that by 2, which gives you... Well, 27.30 plus 27.40 over 2 gives you 27.35, which is our mean titer. Right, part 2 of the question. Citric acid is neutralized by sodium hydroxide, as shown in the equation below. Calculate the mass of citric acid in 1 lime. So yeah, remember, it's 1 lime here. Okay, they've given us the MR as well. So obviously we have to use the this mean titer we worked out here, because the whole point of doing this titration was to work out what volume of sodium hydroxide neutralizes citric acid, and now we've worked out this volume here. So when you work out this mean titer, don't ignore it, right? Don't use 25 centimeters cubed, use this 27.35, because as you can see, this is two parts of a question, right? And 90% of the time you'll have to use the mean titer that you calculated before, because that was the whole point of doing that titration in the first place. So make sure you don't ignore this. 90% of the time when you work out the mean titer, you'll be using it in the part 2 of the question when you actually do the titration calculation. Right, so obviously since we know the volume, we can use N equals C multiplied by V to find the moles of sodium hydroxide required to neutralize. So we can do 27.35 over 1,000 to convert to decimeters cubed, and multiply by concentration, which was 0.8. We'll multiply that by 0.8, gives you, well, we have 27.35 over 1,000 multiplied by 0.8, gives you 0.02188. Make sure you do it to one more significant figure, because usually the answer is 3 significant figures and so on. So say they want the answer in 3 significant figures, you do it to 4 significant. You do your working out in 4 significant figures, so to maintain the accuracy of your answer. So yeah, the 0. That's the moles of the sodium hydroxide, and as we can see, we have a 3-to-1 ratio between sodium hydroxide and citric acid. So that means we're going to have to, so therefore we have to divide the moles of sodium hydroxide, which is 0.02188, over 2, which would give you, not over 2, sorry, over 3. So divide that by 3, which gives you 7.293 times 10 to the minus 3. And since this is now the moles of citric acid, so C6H8O7, but in 25 centimeters cubed. Well, because remember, we said that we pipetted it here. And so obviously to get it back to its original volume, we would have to multiply it by 10. So multiplying 7.293 times 10 to the minus 3 by 10 gives you 0.07293. And since we've got that now, that's the moles of the citric acid. And we know that we can use the equation moles equals mass over mR. So we can say that the moles, which is 0.07293, equals, well, the mass over the ml, which is 192, which they've given us here. And that means the mass would be, well, 192 multiplied by 0.7293, which gives you 14.0032. And obviously this is in 2 limes. Because remember in the question they told us, they squeeze out 2 limes here. This is where they catch you out very easily. And so obviously they put in bold 1. Make sure you read the question carefully, because it will cost you marks. So since we know that's in 2 limes, we know that in 1 lime we can just do 14 over 2, which is obviously 7. So therefore the answer would be 7.00 grams to 3 significant figures. Right, next question, part C. The student's teacher thinks that there's an unnecessary safety risk in using a sodium hydroxide concentration of 0.8 for titration. Suggests how the student could modify the method using a sodium hydroxide concentration of 0.2 instead of 0.8. The student should aim to have the same titer as the original method. So Right, so from this question, we can see that, well, if we have, from 2 limes, we had a concentration of 0.8, right? So in 1 lime, that means we'll have a concentration of 0.4, if that makes sense, by dividing it by 2. And since we know that, well, we want a concentration of 0.2 actually, and we originally have a concentration of 0.8. So we need to dilute the citric acid by a factor of, well, 0.8 over 0.2, which gives you 4. So since we know that, so well, what we have to say is, well, how can we get 0.2? So we know that 1 lime has 0.4, so half a lime, therefore, so half a lime would give you 0.2. So we can say we can use half a lime as it will dilute the citric acid concentration. Well, actually, not dilute in this case. Reduce the citric acid's concentration by a factor of 4 to match the original titer when we use a lower concentration of sodium hydroxide, and therefore it gives a 1:4 ratio between citric acid and sodium hydroxide. Right, next. So the other fruits contain different organic acids. Apple juice contains malic acid, which has the following structure. Right, so it looks like a dicarboxylic acid here. Malic acid can be oxidized with heat using potassium dichromate. Write a balanced equation for the reaction, showing the structure of the organic product and using O to represent oxidizing agent. Right, so since we're oxidizing this, we know that nothing will happen to the carboxyl group, so nothing will happen to those. And what we notice is this is an alcohol, right? And this is a secondary alcohol because the carbon it's connected to, so this carbon is connected to 2 other carbons, which makes it secondary. If it was connected to 1 other carbon, like if it was connected to 1 carbon only, it will be a primary alcohol, and if it was connected to 3 carbons, then it'll be a tertiary alcohol. And we know that tertiary can't oxidize. And so since we know that this is a secondary alcohol, and when we oxidize it with potassium dichromate, it should give us a ketone according to the organic synthesis sheet. So let's write the original structure first. So HOOC, CH2, COH, H, COH. We oxidize that under reflux with acidified K2Cr2O7, and that should give us, well, the ketone now, so HOOC, CH. So the carboxylic acids don't change because they don't oxidize further. And here we'll have the ketone, and we'll have the COH here. And it'll also release water as a byproduct. All right, so yeah, that should be a good 2 marks. Just memorizing the organic synthesis sheet. If a trick that I used to do, I used to put it up on my wall, and sometimes when I would just like look up and randomly, I'll just see the sheet, and it's easier to memorize that way when you put like posters up on your wall. So yeah, that's a pretty good way to, and also get someone else to test you on it, like a quiz or something. And yeah, right, 2. Strontium and calcium both react with water. Write an equation for the reaction of strontium with water. Oh, that was in my A-level exam this year, actually. Damn. Right, write an equation for the reaction of strontium with water. So we have Sr plus water, and gives you strontium hydroxide plus hydrogen gas. And let's go ahead and balance this now. So we know that we have 4 hydrogens there, so we need to increase this by 2. And other than that, this seems to be balanced. Oh yeah, I remember we were working when I had my exam this year. You had to work out Ka with no, was it Ka? No, you had to work out Kw something like that with this, right? And because you know how this is die basic, I forgot to multiply it by 2 and I lost all the marks on the question. I was so pissed. Oh my god! Make sure you multiply by 2. Flipping hell, man. Anyway, part 2. Using oxidation numbers, explain why the reaction of strontium with water is a redox reaction. Right, so if you look at this, we know that originally strontium has an oxidation state of 0. And over here, it has an oxidation state of +2. So we can say that strontium oxidized from 0 to +2. So that's good. And right, let's look at what other things that could be reduced this time. So oxygen seems to remain the same. So obviously it's a 2 minus here and seems to be a 2 minus there as well. So it doesn't seem to be that. Oh yeah, it seems to be hydrogen actually, because if you look at here, hydrogen has a oxidation state of +1 here, right? And over here it's 0. So what we can say is hydrogen is reduced from +1 to 0. And so yeah, that should be it, to be honest. I think it's sufficient just writing the oxidation numbers here and just writing oxidized and reduced to signify. There's no point like writing extra waffle. Right, part 3. Explain why calcium reacts more slowly with water than strontium does. So this should be another like memory recall type of memorization answer. Like whenever you revise chemistry, you'd have this answer like already planned out what you're going to write. So obviously in this case, we'll talk about the number of shells, shielding, nuclear attraction, and so on. So let's go ahead and start with the shells. So what we can say is, as we go down, group 2, there are more shells. And so the electron on the valence shell is further away from the nucleus if we were to consider calcium and strontium. So obviously calcium would have calcium's valence electron would be closer to the nucleus than strontium. I can't be bothered to write that, but yeah, keep that in mind. So actually, let me just write that. I don't know what I'm saying. I can't be bothered. All right, so the valence electron on calcium is closer to the nucleus than strontium. So there's stronger nuclear attraction and so it has a higher ionization energy. Obviously, ionization energy is the energy required to remove the electron on the valence shell and subsequent shells. And also, we can consider shielding as well. There's also more electrons as we go down the group. So calcium would be shielded less than strontium. And that should be it. Make sure you have to write comparisons. You have to say, okay, calcium, obviously, so let's say, in the case of shielding, you would have to like compare it. Calcium's has less shielding than strontium, for example, or nuclear attraction. Strontium's valence electron has a weaker attraction than calcium per se. So make sure you always have to write the comparison for these types of questions. Although you may write the correct point, if you don't write calcium is less and calcium is more and strontium is less, for example, you would lose a mark. Right, so a student adds barium oxide to water. A reaction takes place, forming a colorless solution. Predict the pH of the colorless solution. Right, so barium oxide, when you react with water, it would usually produce barium hydroxide, so an alkali. So we know that alkalis have a pH range of above 7 to around 14. So anything between 8 and 14 should be right. So I'm just going to say 12. But anything between 8 and 14 should be correct for an alkali. But obviously it's barium hydroxide and that's the quite alkali, so it should be, a bit higher than 8. So part 2, a student adds a few drops of sulfuric acid to the colorless solution. Describe what the student would observe and give the formula of the barium compound produced. Obviously, we have barium hydroxide currently in the solution. So if you add sulfuric acid, it would form barium sulfate, because the sulfate would displace the barium hydroxide, the hydroxide ions. So what we'll have is a white precipitate forms, which is the BaSO4. Oh yeah, you have to write it here anyway. So yeah, BaSO4. Alright, question 3a. The student investigates the rate of reaction between zinc carbonate and dilute hydrochloric acid. Equation shown below. So the method is add 50 centimeters cubed of dilute hydrochloric acid in a conical flask. Right, place the tan. Right, so this is just a reaction rate practical kind of question. So the graph shows that the reaction gets slower over time and eventually stops. Explain why in terms of collision theory. Right, so we can see mass decreases, time increases. So we know that in this case, the hydrochloric acid will be the limiting factor, because the volume of the acid will start to decrease, right? So what we can say is, as hydrochloric acid is the limiting factor. Right, so as we know, hydrochloric acid is the limiting factor. So limiting factor. As the reaction goes on, the concentration of the hydrochloric acid will start to decrease. Obviously, this is because the, as we see in the question, the hydrochloric acid reacts with the zinc carbonate to form the zinc chloride. So obviously, it starts to decrease, which is obviously illustrated in this graph. So we'll start to decrease as it reacts with zinc carbonate. And as we know that, so therefore there'll be less HCl molecules, and so there are less frequent successful collisions. So obviously, there are less frequent successful collisions, and eventually, as the HCl is used up fully, the reaction stops, as there's no more frequent successful collisions. Right, that's that. So using the graph in figure 3.1, find the rate of reaction in grams per second at 50 seconds. So obviously, as it's a curved graph and we want to find the, it asks us to find the rate of reaction, we'll have to... Alright, so I've recharged my pencil now. So we can just go ahead and attempt this. So attempt to draw a tangent at t equals 50. So we know that 50 CS, so it would be roughly at this point. So we need to draw a tangent at that point. So if we were to perhaps start from like here maybe, go downwards like so. Oh no, that's a bit too steep actually. Free to go, well, nothing. That should be all right, I guess. And in that part can just go up like that. Right, so let's find the change in y and change in x. So the change in x first, so we can see that delta x would be, as it goes up in 5, so it'll be, that's 210, that's 220, that's 225. So roughly 230 will be the change in x. Alright, now, so that's change in x. So change in y would be, 92.32.34, 92.35 minus 91, which gives you 1.35. So now we can just do change in y over change in x. So change in y was 1.35, change in x was 230. So over 230 gives you 5.9 times 10 to the minus 3. Alright, so yeah, that should roughly be the rate. Obviously, they allow a range, and in this mark scheme, they said they allow a range from 5.7 times 10 to the minus 3 to 6.9 times 10 to the minus 3. So if you basically draw a tangent and you're within that range, you should be fine, to be honest. So what we know is the reaction will be 5.9 times 10 to the minus 3. So the next part of the question states, the student repeats the experiment but heats 50 centimeters cubed of dilute hydrochloric acid up to 40 degrees centigrade before adding the zinc carbonate. So obviously, as we have a high temperature, it would have a high rate of reaction, so the hydrochloric acid will be used up more quickly, but the reaction would finish earlier on. So obviously, this can be represented by drawing a steeper curve, but obviously it will level off at the same mass. So if we were to, what we'll need to do is obviously make it steeper, the initial rate. So if we were to go ahead and probably do something like this, but it like plateaus sooner, but it like levels off around there. So obviously something along these lines where the initial rate is steeper, but it levels off same. So something along those lines. To be honest, it probably might be a bit more steeper here. So it might be a bit more steeper there. But for argument's sake, basically something similar to this, just make the initial rate steeper, but make sure it plateaus earlier on. Let me actually retry this one more time. Let's see if we can probably make a better one. So if we were to make it steeper, or to plateau it here, maybe. Oh no, it's joining that line. I probably shouldn't do that. Something like this. You know? Yeah, something basically along those lines. But yeah, wait. Yeah, so something like that, but it plateaus like earlier on, like it plateaus here. So yeah. Essentially that. Sorry for the bad drawing. I'm not that good at drawing graphs, but essentially make sure the rate is steeper. Make sure it plateaus at the same mass, because although it happens faster, the moles and everything else kept the same, so the mass would be the same of the product. Right, so that's that question. So B, the student investigates the reaction between zinc and dilute sulfuric acid. So here we have the student adds a piece of zinc to each of the test tubes. The student adds a few drops of aqueous copper sulfate to one of the test tubes. From a pale blue solution, the student adds an excess of dilute sulfuric acid to each test tube. Describe two differences the student would observe between the test tubes. Right, so obviously so as one of them is essentially has the copper 2 sulfate catalyst and one does not have the copper 2 sulfate catalyst, the one with the catalyst would have a high rate of reaction. So what we can say is that, first of all, zinc will dissolve quicker in the test tube with the copper 2 sulfate catalyst. It should just be CuSO4. The same test tube that has the catalyst will have more vigorous effervescence. The effervescence is basically bubbling. Or, no, actually not bubbling, like fizzing. So yeah, effervescence. So yeah, that's that. So part 2, using the axes below, sketch an enthalpy profile diagram for the reaction with and without the catalyst. So obviously when you have a catalyst, the activation energy will be lower. So that's one point that we need to remember. Activation energy will be lower. Second point, what we need to look at is, well, is this a endothermic or exothermic graph? And so if we have a look at the reaction here, what we can see is negative 140. So from that we can tell it's an exothermic graph. So the enthalpy change will obviously be negative, and so when you draw the arrow for the enthalpy change, it will be upside down. So if we were to have a go and draw that way, so let's draw it without the catalyst first. So the normal activation energy, it will be higher. So you can probably draw another line down here. And make sure you write your products as well. So like as if like they wrote the reactants there. So we can say ZnSO4 and hydrogen gas. So if you were to go ahead and draw that profile first, it'll look something like that, I guess. And what we have is the activation energy. It goes up like so. So this should be actually let me like color coded. So this should let's make that red. And we'll say that's the original activation energy because that's what they told us to use for the one without the catalyst. And now let's draw the profile with the catalyst. So it will be something like this. And from this, what we can see is that this should be EC. So the one with the catalyst, and we can see it has a lower it has a lower activation energy. And then we can just draw the enthalpy arrow. So if you just go ahead and make the line, what we can say is that the arrow goes downwards as so. And this should be our enthalpy change. So when the enthalpy change arrow goes downwards, that means exothermic, and when it goes upwards, it means endothermic. And so yeah, so when you include the energy profile diagram, so this and this, the label the activation energies in the correct arrows at the top of the peak, and you have the arrow for the enthalpy change, that should get you all 3 marks. And also writing the product as well. Make sure you don't forget the products. Right, question 4. So here we've got a nice Le Chatelier's principle question. So in industry, hydrogen is manufactured from methane, as shown in equilibrium 4.1. So we have methane plus water makes carbon monoxide and hydrogen it's an endothermic reaction. The industrial process is carried out at 15 atmospheres pressure and at a temperature of 800 degrees centigrade, uses an excess of steam. A nickel catalyst is used. Explain why these conditions are used industrially. Right, let's start with the 15 atmospheres of pressure. So obviously when we say 15 atmosphere of pressure, to be honest, when you have an increase in pressure, it would go to the side with less gas moles, and when you have a lower pressure, it goes to the side with more gas moles. And 15 atmospheres of pressure is quite a low pressure. So what we can say is, as 15, so let's actually set our answer. Let's start with pressure first. So pressure, as the pressure of the reaction is 15 atmospheres, so ATM, the equilibrium will shift to the right. This should be position actually. The equilibrium position will shift to the right due to that side having less gas moles and also the pressure is low. Right, so shift to the side with more gas moles. So that's pressure. So now we can look at temperature. So obviously when we have temperature, you have the focusing on equilibrium here. So when you have a high temperature, like 800 degrees, for example, it will shift to the endothermic side. And as this forward reaction is endothermic, we know it will shift towards the carbon monoxide and the hydrogen, so increasing its yield. So as we have a high temperature, the equilibrium position shifts to the endothermic side, which is the right, which is not the right actually, the forward reaction. So the yield of carbon monoxide and hydrogen increases. Right, so that's that. Also, we can also talk about the rate of reaction for these, because obviously what we have is a high temperature, which increases the rate. A catalyst which also increases the rate, but a low pressure, which decreases the rate. Because when we have low pressure, we have a larger volume and less gas moles. And so what that means is there's going to be less frequent successful collisions, right, which reduces the rate. That's why when you have a lower pressure, the equilibrium shifts to the side with more gas moles to increase the gas moles in order to kind of match the pressure that's surrounding not the pressure, to match the volume. So what we can say is temperature, so the high temperature increases the rate of reaction as there's more kinetic energy within the molecules. And so there are more frequent successful collisions. Frequent successful collisions. So we know that. And we can also say the catalyst also increases rate. Because the way the catalyst increases rate is because it provides an alternative pathway for the reaction to occur. And that alternative pathway leads to more frequent successful collisions. So we can say alternative pathway I'm not going to write frequent successful collisions. I'll just use these apostrophes to basically mark that we're saying the same thing. So we know that, and well, pressure, as the pressure is low, there is, well, less frequent successful collisions. So again, I'll just put the quotation marks. Right, so obviously now we know that. So we can see, well, it increases so we focused on the yield at first. Then we focused on the rate and how it benefits the rate. But now what we have to look at is, well, like the more economic and safety sides of things. Well, if you have a high temperature, so if you have a high temperature, more energy is required to heat, no, to increase temperature actually. So there's going to be more costs and increase in costs. And also what we can say is that as we use as we don't use a high pressure, it's more safe. Because if you have a high pressure, there's a high risk of exploding. And obviously we use a catalyst, so the activation energy is lower, so that means less energy is required to, well, start the reaction, and so it will cost less. So I won't write that down, but I just explained it, so I'll put another apostrophe there. So right, that should be that. So next, part 2. A chemist mixes methane and water and leaves the mixture to reach equilibrium. So, right, so this is a Kc question. Right, an expression for the Kc constant and calculate the numerical value. So when we write Kc expressions, like as you've seen in the paper 1 walkthrough, it's just the products over the reactants, and any the number of moles of the product, like say 3H2, the 3 will be raised to the power of the concentration of that gas. And they've given us the concentrations here, so we don't have to they haven't given us moles, so we don't have to divide by volume or anything. So we can say that, let's write the expression first. So Kc equals H2 cubed, for the concentration of Hg cubed, multiplied by the concentration of carbon monoxide, over the concentration of water, multiplied by the concentration of methane. And since we have that now, what we can do is you can say 1.53 cubed, multiply that by the concentration of carbon dioxide, which is 0.51, over the concentration of water, which is 0.682, multiplied by the concentration of methane, which is 0.111, which gives you 1.53 cubed multiplied by 0.51 over 0.682 multiplied by 0.111 gives you 24.13. So that's our value of Kc. So 24.13. So yeah, that should be our value of Kc. So let's run 3 significant figures, because in the table we see they use 3 significant figures. So you want to match the same the same accuracy as they've told you in the question. So in this question we notice that it's up to 3 significant figures. So I left answer as 3 significant figures as well. Right, part B. Hydrogen can also be manufactured by reacting ethanol with steam, as shown in the equilibrium below. So yeah, calculate the bond enthalpies. Again, this should be pretty simple. Usually in the A-level paper, they will not like draw out the displayed formulas for you. They'll just like give you the reactions. So for example, it won't be 3HOH, it will just be like 3H2O. And then obviously you'll notice that there is 2 bonds here. And so yeah, anyway, let's work out the bond enthalpies. So let's start with C to H first. Let's see how many there are. So there's 1, 2, 3, 4, 5. So there's 5 altogether between the reactants and the product. So what we know is going to have 5 multiplied by 415. So let's do the reactants first, because obviously you could use Hess cycle, but obviously I use the formula. I had to stop saying obviously. So obviously, oh my god. So we're going to use the enthalpy change of the products minus the enthalpy change of reactants to give us the overall enthalpy change. So we have 5 multiplied by 415 plus, well, okay, let's look at how many OH has. So we did look at C to O now. So C to O is 358, and so we know that. Plus O to H, which is 464. And obviously, if we look at these two, we know there's going to be 2 here. So 2 multiplied by 464. But there's 3 moles of that, so we'll multiply that by 3 as well. So overall, the enthalpy change of reactants, if I put that in my calculator, will give us 5 multiplied by 415 plus... I also forgot the carbon-to-carbon bond as well, so that should be plus 347. So be 5 multiplied by 415 plus 347 plus 358 plus... well, since we have 2 of those bonds there, and then, well, we can multiply that by 3 as well. So that means we have 6 of those OH bonds. So what we can say is we have 7, including the other one. Because, well, there's 6 from the water, and there's 1 from here, so that'll give us 7. 7 multiplied by 464, and I think that should be that one. So that would give us 6,028 for the reactants. Now for the products, let's do that. So we have 6 of the H to H. So we know that H to H is plus 435, so we're going to have 6 multiplied by 435. And then plus, well, if you look at the carbon dioxide, we have 2 carbon to oxygen double bonds. So we can have, well, obviously since we have 2 of them, but we also notice there's 2 moles, so it will not be 2. It will be 4 multiplied by 805. So you know the enthalpy change of products will equal 6 multiplied by 435 plus 4 multiplied by 805, which gives us 5,830 kilojoules. And since we know that, we can just sub it into this formula here, which is enthalpy change of products minus enthalpy change of reactants. So we know that products is 583 and reactants is 6,028, which gives us minus 198, which is the enthalpy change. So this should be our answer, minus 198. But obviously, since we know that this is a this seems to be a endothermic reaction, doesn't it? Actually, yeah, since you know this is an endothermic reaction, because they've told you in the question here, since you know it's a endothermic reaction, you can just put a positive here because we know it's going to be plus 198. So although this formula might not work, it might give you the wrong sign, but just double check in the question if it's positive, if the enthalpy change is positive or negative. So in this case, it's positive because it's endothermic. Right, next. Carbon dioxide and water molecules have different shapes. State the bond angles in carbon dioxide and water molecules, and explain in terms of electron pair repulsion why the bond angles are different. So when we look at electron pair repulsions, we look at the lone pair to lone pair repulsions. We look at the lone pair to bonding pair repulsions. So lone pair to bonding pair repulsions, and we look at bonding pair to bonding pair repulsions. So let's look at carbon dioxide first. So the carbon CO2, well, it has a bond angle of 180 degrees because it's a linear. So So yeah, the shape would be linear. And so we know that it has, it has two double bonds. And yeah, so that should be that. And next what we have is the, so essentially all it has is two bonding pairs and no lone pairs. Right, next is water. So water, we know, is going to have a bond angle of 104.5 degrees. You know, the shape is going to be bent. You could say V shape also, but I think I'll just go with bent. And obviously water looks like this in it. So we have the lone pairs here on the oxygen, which has the which essentially repels the hydrogens. So what we can say is that it has two lone pairs and two bonding pairs. The lone pairs repel the bonding pairs. Repels the lone pair of electrons. On hydrogen to 104.5 degrees. So yeah, that should be that. And also the lone pair repulsions would be stronger than the bonding pair repulsions. Right, so that should be that. Next, 2-bromobutane, it can be prepared by 3 different methods, and it give us the MR there. 2-bromobutane can be reacted by reacting butane with bromine. The reaction is initiated by the form of bromine radicals from bromine. So obviously this is free radical substitutions, and we know that we need ultraviolet or UV light. So we can just say we need UV. Next says, why 2 equations for the propagation steps in the mechanism. Right, so in the initial steps, what we have is the bromine will go from Br2, and when you add the UV, it will go to 2 bromine radicals, right? So that's the initiation step. So we have the hydrocarbon plus the bromine radical would produce, the hydrocarbons radical, so CH2, CH3, CH2, CH2 radical, and plus hydrogen bromide, because one of the hydrogens from the hydrocarbon would go to react with the bromine radical, leaving us with the hydrocarbons radical. And since we have that, we have CH3, CH2. Actually, we made that in the wrong position, because in the question it states the bromine should be here, so we know that this carbon will lose its electron, so it will be CH3, CH2, CH. We could put the radical here, CH3. And since now we know that, I should probably put that above the carbon. And so plus the HBr. And now we have that, we can do CH3, CH2, CH radical plus CH3. And that reacts with the Br2. And that will give us CH3, CH2, CH Br, CH3 plus a bromine radical. That's because obviously this bromine radical would react with the other hydrocarbon again, so it would react with this again. That's why it's called propagation. It propagates another one. So yeah, the yield of 1-bromobutane, 2-bromobutane is only 30%, so just two reasons why. So because when we have free radical substitution, there's no guarantee it will, obviously, the bromine would substitute this second carbon's hydrogen, right? It could replace this hydrogen on this carbon or the hydrogen on this carbon. There's no guarantee. So, and also it could substitute, well, more than one, it could substitute more than one hydrogen. So it could be, I don't know, 2,2-bromobutane or 2,2,3-bromobutane, you know? There's no guarantee on which on which one it would substitute. So what we could say is further substitution of hydrogens in the chain which may produce a compound with more than one bromine, so greater than one bromine, that kind of sphere here. And obviously, so second reason might be is the bromine substitutes in different positions. So it could substitute in the first carbon, second carbon, third carbon, etc. Right, so part B states 2-bromobutane can also be prepared by reacting butene with hydrogen bromide. So we've got butene plus hydrogen bromide makes 2-bromobutane. Explain in terms of atom economy why reaction 5.2 is more stable than 5.1. Sustainable by 5.1. So let's work out the atom economy of 5.1. So the all the thoughts in the previous question was around 60-something%, I think. Oh no, it's 30%. That was the percentage yield actually. So to work out the atom economy of 5.1, we need to do the MR of the desired product, which was 136.9, over the MR of all the products. So 136.9 plus the hydrogen bromide, which would be 79.9 plus 1, which would be 80.9. So we have 136.9 plus 80.9, which gives us 217.8. We'll put a reaction 5.1, and that multiply that by 100 to convert it to a percentage. To multiply by 100 gives us 136.9 over 217.8. That gives us 62.8558, which would be 62.9%. And if we were to do it for 5.2, the atom economy would be, what was the MR of the product? So the MR of the product would also be 136.9 over the MR of the reactants. Obviously, as this is electrophilic addition, there's no other product, because the hydrogen bromide will go into this and nothing is displaced within this. So everything will remain the same. It's just joining onto this. It's not displacing anything. So there won't be any extra product, like an extra hydrogen as a product, for example. That's why. So, like, if you were to draw out the reaction mechanism, you would understand what I mean. So that means that the MR of the reactants will also be 136.9 in that case. Multiply that by 100. That will obviously give you 100% atom economy. So you can say that so for 5.1, atom economy is less than the 5.2. So part C, 2-bromobutane can also be prepared by reacting butane to wall with sodium bromide and sulfuric acid. A student plans to prepare 10 grams of 2-bromobutane using reaction 5.3. Percentage yield is 67%. Calculate the mass of butane to wall needed for this preparation. So first, let's work out the moles of 2-bromobutane, as they're giving us the mass here, and they've also given us the MR, which is over. They gave us the MR, didn't they? Yeah, 136.9. So we know the MR is 136.9. So we can say that the moles of 2-bromobutane is equal to 10 over 136.9, which gives us 10 over 136.9 gives us 0.07305 moles. And that's what we need. So you can assume that this is the actual moles that we need, because you remember the equation for percentage yield is actual over theoretical multiplied by 100. So we know this is the actual moles, so we can say that 0.07305 over the theoretical moles, multiply that by 100 equals 67%. So we can multiply theoretical on that side, and we can divide by 67 to give us 0.07305 multiplied by 100 over 67 gives you the theoretical mass, the theoretical mole, sorry. So since we've got that, we can multiply that by 100 over 67, which gives us 0.109. And now we have 0.109. What we can do is we can multiply the theoretical moles by the MR of the butan-2-ol, due to it being a 1-to-1 ratio between the butan-2-ol and 2-bromobutane. There's no point multiplying or dividing to match some sort of ratio. It's 1-to-1. So we can just multiply it by the MR of butan-2-ol, which is 15 plus 14 plus 13 plus 17 plus 15, which is 74. So if you multiply that by 74, that'll give us 8.07 or 8.066, and three significant figures will be 8.07. So that's that done. So pot 2, the student mixes butan-2-ol, sodium bromide, and sulfuric acid in a pear-shaped flask and refluxes the mixture. After 1 hour, the mixture in the flask has separated into 2 layers, an aqueous layer and an organic layer. Describe the procedure you would need to carry out to obtain a pure, dry mass of 2-bromobutane from this mixture. So obviously this is a separating funnel. A separating funnel essentially kind of looks like a pear-shaped flask kind of thing. So this is, actually, let me see if I can draw. Actually, I'll just insert an image of a separatory funnel now, and that's what it looked like. So what we need to do is, first, we use a separating funnel to separate the aqueous and organic layers. So basically, the way this works is obviously the liquid or layer with a lower density will be found above the one with a greater density. So let's say if you had a compound which had a greater density, then the one with a lower with another compound with a lower density, the one with the greater density will be found at the bottom of the separating funnel. So, and obviously this only works with immiscible liquids like organic liquids and so on. So that separates, and then obviously we can dry the organic layer with an anhydrous salt. Such as calcium chloride. Then we can distill it, and you can collect it at its boiling point. And have they told us the boiling point anywhere? Yeah, 91 degrees. And yeah, that's part 2 done. Right, so question 6, the organic compound A is unsaturated and is a trans stereoisomer. Compound A has the following composition by mass, so 55%, 8% of carbon, 7% of hydrogen, and 37.2% of oxygen. The mass spectrum and the infrared spectrum of compound A are shown below. Also here we've got his mass spectrum and it's infrared. User information. So this is your typical infrared mass spec question. If you practice these enough, it's pretty simple to get 6 marks. So yeah. So when you see percentages here, you're instantly going to want to work out the empirical formula. That'll give you a quick 2 marks guaranteed. And it's a pretty simple part of the question. So let's go ahead and do that first. So let's do carbon. So it'll be 55.8 over its MR, which is 12, which gives you 55.8 over 12, which is 4.65. Hydrogen, it's 7 over 1, because the MR of hydrogen is 1, which gives you 7. Then oxygen was 37.2 over 16, which gives you 2.325. Right, so the smallest number is 2.325, so we divide all the numbers by 2.325. So if you do carbon first, you have 4.65 over 2.325, which gives you 2. Hydrogen, you can do 7 over 2.325, which gives you 3.01, so we can just say 3. And oxygen gives you 1, because 2.325 over 2.325 is 1. So now we've got that, we know it's going to be C2H3O. Now let's work out the MR of this. So the MR of this is 24 plus 3 plus 16, 43. If you look at our mass spectrum, the highest peak, the peak with the strongest intensity towards the end is usually what the MR will be. So the one found here, which is 86, this would normally be the MR of the compound. Sometimes you may have little fragments after it. These may be due to isotopes of hydrogen, for example, like deuterium, or that might be the case for that. But most of the time, the one with the highest intensity found towards the end of the spectrum is your MR. So in this case, this is the MR, which is 86. And this is 43. So to get to 43 to 86, we just need to multiply by 2. So we multiply this by 2. So you get C4H6O2. Now this is the formula of our compound. Now we've worked out, we can look at the spectrum to see what functional groups are involved. So if I go ahead and work this out quick, we have this peak here, this broad peak. And when you see like a broad peak like this in between the ranges of roughly 2,600 to 3,300, you instantly know that's going to be a carboxylic acid. And this broad peak here is obviously due to the OH found in the carboxylic acid functional group. So if I draw out the carboxylic acid functional group quickly, it's due to the OH found here. Now, let's see this peak here. This peak is found roughly in 1,000, so roughly 1,650 to 1,700, around that range. And in that range, you would normally find a carbonyl, right? But obviously, there's no carbonyl in this compound because we determined it was carboxylic acid. Well, this is due to this part of the carboxylic acid, the C double bond O. That's the reason you get that peak there. And then they've been quite sneaky with this infrared spectrum, such that they actually have included another peak right here. If I just quickly rub out this arrow here, this is another peak right here. And so if you look at that, that's roughly around 1,000, so 1,650, it's around that. And if I look at the formula booklet quickly, if we load that up, you can see that in this range, we would normally find a alkene functional group, so C double bond carbon, which is found in the 1,620 to 1,680 range. So now we've identified these functional groups. These are just signature peaks, and we don't really need to look at them. Right, so if we go ahead and draw the compound quickly. Actually, let's write down what we found in the analysis. So first, let's look at the carboxylic acid, so infrared analysis. What we found first is the COOH. This is found in the 2,500 to 3,000 300 range. So for this, all you want to do is look at your formula booklet and just write down the range at which you found it. Once you've identified the carboxylic acid, just write down the range of the carboxylic acid. So this is due to OH in COOH. Then you have the carbonyl, which is found in the range of, again, in the formula booklet, carbonyls are found in 1630, well, the C double bond though, not really carbonyls, to 1820. And this is also due to CO in COH. And then you have the C double bond C, which is found in the 1620 to 1680 range. And yeah, so now we've got those. Now let's go ahead and try to attempt to draw the compound. So there's 4 carbons, so let's draw in those 4 carbons first. So 1, 2, 3, 4. We know that one of them is going to be a double bond. So let's go with the over here for now, because we understand that it's a trans isomer, right? And if we were to have, actually I might explain that later. First, let's draw out the compound. Then we have the COOH here, and then we have our methyl group here, then hydrogen here, hydrogen here. Right, so if I were to draw this such that it looks like this, so H, and you have the COOH here, and then you have the methyl group, and then H. Obviously, we know this is going to be, first of all, this won't be EZ isomerism, and we know this is cis and trans isomerism because there are 2 sol, so 2 hydrogens by itself in the compound. And so so we understand that this is going to be cis and trans. So, but if there was, say, there was only 1 sol hydrogen, say this was another CH3, this would be a E isomer because, well, there's 3 different groups and there's only 1 sol hydrogen. And so in EZ isomerism, there may be no sol hydrogens, or there only be 1 sol hydrogen. But in cis and trans, there will be 2 sol hydrogens, as so. And obviously, the heaviest groups are found on the opposite sides. So the COOH and the methyl group are found on opposite sides. So this is going to be a trans isomer. And also, if, say, you understand that the double bond is going to be from the second carbon, because if you were to do it from the 3rd carbon, as so, and we had the H here, and then C, and then let's quickly draw in the hydrogens, then the carboxylic acid, and we were to write it as so, hydrogen here, and you have the CH2COOH. This will not be cis and trans because there's 3 of the same group. There's 3 hydrogens this time. And there's only 1 of this. And so you can't really compare it. I mean, not really compare, you can't really use cis and trans in this sense. It has to be 2 different groups in order to be able to be trans. And so in this case, you know that the alkene will be at carbon 2. So yeah, so this is what our compound will look like. And yeah, so that's it for this question. And I feel like, yeah, this is the end. So overall, this paper was quite good. It was harder than the first paper, definitely. But it wasn't too bad, to be honest. I think some questions were difficult, some questions were easy. But overall, a good paper, but a bit harder than paper 1. So yeah, if you guys did enjoy this video, don't forget to like this video and subscribe. Also leave a comment if you want me to do other chemistry papers from different exam boards, or I don't know, any other chemistry paper. I'm also going to, after this, I'll probably start doing the 2022 A-level papers because these are the AS papers. And so yeah, I'll probably do the rest of OCR, then probably do the old spec. So yeah, if you guys did enjoy this video, don't forget to like, subscribe. Thank you for watching. Goodbye.